Thanks, Luke and Nina, and appreciate everyone being here. I'm really grateful and sort of honored with this opportunity. It's really nice to be able to talk to you about a topic that has been such a big part of my life for a lot of years, and also to be the first speaker, because what that means is whatever questions you ask afterwards, I've got the rest of the week to fact check what you're doing, to Google you and all that, so just be careful. So I want to really try and give you sort of a broad picture, sort of my observations of where we've been and where we're going. And the idea is to get you thinking about things that we'll be doing in the breakout session. So really my goals then, the first is to talk a little bit about how the science has, how it's developed, what it's been focused on, a little bit about how it's changed over the years. And then really what we're getting at is the breakout session this afternoon has this topic of what do we know and what are our uncertainties? And really that's the big goal of the conference. And so again, I won't be hitting everything, but if there's a gap that you see, please write it down. So if you find yourself thinking, wow, that's interesting, I wish he would have talked about this. Well, write that down. And so the goal is really to generate topics for discussion. And so a couple of caveats. First of all, unavoidably what I'm talking about is going to be focused on my research. It's stuff that I've found interesting and important over the years, and I still do. And so these are topics, at least through my filter, that I'm going to be presenting this from. And so along those lines, if I'm going along and you see something that you have done that I fail to talk about, well, first of all, I apologize for my oversight. Or another way to look at it might be that what you did is so groundbreaking and unique that I just wasn't even aware of it yet. So give yourself gold stars for that. And in fact, you've got stars in the back here. Maybe that's what they're for. I'm not sure why they have those. So to begin with, I'd like to point out a book that just came out a few weeks ago.
It's a great book.
Oh, good. Thank you. And if for $170, it can be yours. But there's 19 chapters, it's 600 pages, and just some really nice work by the authors. This may be the last publication that Matthias Jakob will have his name on. And so we're just really proud to have done this. And Scott McDougall put a huge effort into this, and I kind of went along for the ride and helped out where I could. So that's available now, and hopefully it will be something that's very, very useful to people. So to start this out, I wanted to look at just this kind of sense of when did post-wildfire debris flows take off as a topic? Well, thanks a lot, Luke, for already commenting on this. But I went through and just said, okay, let me look at sort of 5-year increments and just see how many publications we had over the years. And so you can kind of get a sense of how this sort of progressed. I use the topic post-wildfire debris flows. It actually captures a lot of smaller terms other than just that, that exact phrase. But there's still some questions as to, is this the right research term? And the second is this really just a reflection of the fact that we have a lot more publications in general? There's a lot more journals in general, so maybe it's inevitable that it's going to look larger over the years. Or maybe we're just capturing more recent publications better than older publications. So I said, well, to normalize this a little bit, let me just compare it to a general other topic and see how that's grown. And so I picked geology of California as the other topic. Much larger, you can see there's a similar increase. Don't ask me why it's dropped off those last few years. Maybe the California Geological Survey has gone to sleep, I don't know. But we'll see. So this is a challenge laid out there. It still needs to be normalized though, right? Because there's a lot more. We started with a bigger number. So I said, let me take each of those curves and just divide it by the first period and say, okay, this was our baseline. Let's divide it by that. So how many times more publications do we have recently as compared to that 1961 to 1965? So when we normalize it, here's what it looks like. So Geology California has really doubled, maybe tripled in the number of publications, and I'll just use that as a general geological, geomorphological sciences increase over the years. Compared to post-wildfire debris flows, which has increased, let's say, 350 times. There's a little drop off at the end because we didn't capture everything from 2024 yet. But this has really taken off, and the time period when it sort of launched looks to be like the very early 90s. And so there's sort of a block there when suddenly this, as I'll show you, this has been on people's radar, but it hasn't really had a lot of science, hard science, I'd say, done, published in journals until sort of that time period. So what did we know then at the beginning of the push, at the beginning of this increase? And so I took, as sort of a snapshot in time, I took a John McPhee book. Everybody loves John McPhee, right? If you don't, you will when you look him up. And so this was from The Control of Nature, which he basically published a few stories that he had already put in the New Yorker. And so here is the snapshot that's 1989, which probably is really news from, I'd say, 5 to 10 years earlier, right? Because he's interviewing people who are experienced. Maybe it's not the most recent stuff that's coming out. So I would say this is kind of what was known in, let's say, the early to mid 80s. First of all, they quote things from the Los Angeles Basin about this fire flood sequence. So there's already this sense, and actually it goes back a lot longer than that, of there's a fire and then the flooding is worse afterwards. And there's, they recognize that there's an increase in available sediment, that the rainfall runoff is different, that chaparral communities are unique, that something has to do with how flammable they are and what the recovery looks like. This importance of dry ravel, they're already talking about it at that time period. The role of fire suppression in affecting this hazard, the idea of hydrophobic soils. And they actually refer back to some reports from the early 1930s that talk about the fire flood season. So there's a long time period when people, at least in Southern California, are aware of this connection. And maybe there's not a lot of publications, as we saw, on it, but there's a lot of awareness. I thought this was an interesting quote. This was him interviewing someone, and I can't remember, the employee was from a state agency, but it said, if you don't have a fire, you could go 50 years without a flood. And so they're saying, yes, there are flood risks, but they're much worse after a fire. So how did the focus change over time? And so what I wanted to do, again, is to take some snapshots at a conference series that's near and dear to me, which is the Debris Flow Hazard Mitigation Conferences. And they occur every 3 to 4 years. And so I wanted to look at what are people talking about in these conferences. So we have these little time blocks, recognizing that the location of the conference may affect what the general focus of the presentations are. So the first one, 1997, was in the US in San Francisco. There were no papers that dealt with post-wildfire, that dealt with fire. So, you know, even though we're sort of, let's say, 5 years into this increase in publications, it hasn't made it to this level. The next conference was in Taiwan, and there was one paper that dealt with post-fire debris flows by Sue Cannon, and the response was the title was Debris Flow Response of a Southern California Watershed Burned by Wildfire. And so what Sue looked at was a number of basins that had fires and said, look, there's 30 of them that had debris flows. And so we're early on in science, right? And so there's been this recognition of everything over time. And now someone is trying to say, well, it's not happening in all the basins. Why not? And can we distinguish some of these? And so she measured that there was actually a threshold slope, or average basin or channel slope, where you're starting to see this. That there was that it was affected by the presence of a water repellent layer, and there might be some relation to rock type. And so it's kind of fun to look at this and say, all right, this is how someone is recognizing a topic is important, and these are the kind of the early stages of the things that we're looking at. Defining what's going on, trying to figure out the distinguishing factors between yes and no, and working towards deeper science. So that was in 2000. The next conference was in 2003 in Davos, Switzerland. And there was, again, one paper on post-wildfire debris flows. And it was Sue Cannon, but look, et al. She's got other people involved. So there's other people dealing with this. The title was Wildfire-Related Progressive Sediment Bulking. So now starting to recognize, look, these things are growing in transit. Can we get a handle on what's happening there? And so they were looking at controls on sediment bulking. A few years later, the meeting was in China. There were no papers. Maybe that reflects just the location and who was able to attend the meeting. And then in 2011 in Italy, there were 3 papers. One by Kevin Schmidt from the USGS, looking at hydrology and LiDAR scanning. The next one by Jason Keene and Dennis Staley, also with USGS, talking about the hydrology. And then the third paper by Joe Gartner and other authors, Joe's here, and looking at post-fire hazard assessments, but looking at it by grid cell. So we've already gotten to the point where we're looking at it by basin, but now we're starting to sort of slice up the science into more meaningful and smaller bits. And then there were 12 additional papers that mentioned fire effects or cited post-fire debris flow papers. And so we're starting to see, at least from this sort of snapshot over time, we're starting to see there's more awareness and more breadth in what's happening. A few years later, the conference was in Japan. No papers on post-fire debris flows. And then in 2019, we held the conference in Colorado, and I was one of the hosts with a number of other people. And there were 14 papers, and look, they finally include non-USGS authors, at least from this perspective. And then a dozen papers that cited other ones, and so we're really seeing a lot more here. And I want to just very quickly summarize some of these topics for the papers to get a sense of where we've gone from sort of just describing this process and look, they grow as they're in transit, maybe hydrology is important. And now we're getting to the point where we have run-out models, let's test the accuracy of the models and really try and improve our ability to do this right. Comparing models for simulating inundation, looking at very specifically at rainfall intensity and triggering. And these are all things that we recognize now are important, but seems to be, maybe this stuff has been researched for a few years and now it's showing up at this conference. So you get a sense of how it's maturing as a field. And then changing soil properties during the fire and how that affects the rainfall thresholds. And a lot of you are thinking, that was my work, or that's stuff that I'm doing. And so we're starting to recognize what's important to us in these. Linking these with reservoir hydrodynamics, looking at water and sediment budget. There's been some suddenly that now we're looking more at risk or hazard zonation. How do we manage these hazards? And then I thought this was a particularly interesting one where they did fan trenching and looked at just this huge history of the importance of wildfire in this sequence of debris flows that's creating this alluvial fan. Then hazard mapping, classification, looking at pipelines and communities. So now we're really dialing into the effects on communities and from a hazard management standpoint, how do we manage this particular avenue of effects. And then something I think has been huge is really linking this with the Weather Service and looking at weather radar as a proxy for rain gauges, and also to give us a few extra minutes in figuring out what's going to happen and maybe helping respond to it better. And then there was a paper looking at, again, satellite radar interferometry to detect sediment accumulation. So you can see how the science is getting more sophisticated. And then last year in Italy, there were again a dozen papers, and this is 12 out of maybe 100 to 120. So we're talking roughly 10% of the focus on these general debris flow conferences has been on post-wildfire issues. One on constraining volume measurements. So recognizing that's something that we've been using over time, but it's time to get it more accurately. So you can just see how much the science is maturing. Integrating meteorology and geomorphology, so similar things that we've been hearing before. Discharge thresholds, using machine learning instead of location-specific rainfall records. So that's been one of the weaknesses, is that you need rain gauges nearby at a similar elevation that you think represent the entire drainage basin. And so machine learning is a good way to account for some of those differences. Forecasting inundation, forecasting the spatial location in relation to rainfall anomalies, and then issues with climate change, looking at the future, specific event differences considering climate change. This is an awesome paper. This is my paper. And then post-fire debris flow erosion rates, triggering rainfall intensities. And so you can kind of get a sense now, we're starting to see, I'd say, similar sophistication of topics, but in broadening out into different areas. So the organizers put a few questions before me to just sort of contemplate in this presentation. And one was, what do you think are the open questions about post-fire debris flow hazards? And I want to divide this up a little bit. I want to talk about then, maybe 10 to 20 years ago, and then some changes and things that have allowed us to do different research, and then where that's led us to today. So then, it felt like there was more of a focus on sort of the mechanics. How big are these going to be? What's the discharge? What's the velocity? Impact forces? There's all sorts of sort of engineering related parameters that we've put a lot of effort into trying to predict or trying to understand better. And part of that involves assembling databases and just generating better field data and things that we can work from. I'd say there's basic design of some of the mitigation measures, and particularly things like berms and basins, and trying to figure out what size do they need to be, how much do they need to resist, what sort of run-up might there be. And then really looking at the effectiveness of some of the mitigation methods. And there's some really nice stuff coming out of the Forest Service, looking at the advantage or disadvantage of mulching and seeding and other treatments that might reduce erosion, and how do we optimize that. And then trying to understand things like this channel scour or the growth or the bulking factor, and how does the debris flow change as it's traveling. And then what does the recovery look like? How long? And are there ways to improve that? Predicting hazard levels, how do we break this up and help people understand where they need to be worried about things and how that's changed post-fire. And then rainfall thresholds are just a really key thing to have, and they're so location specific. It requires either a lot of data or somebody's got to develop a method that can work over larger areas. So what sort of tools and approaches have we had over time that can change what we're doing? So one of the things that's affecting this is climate change, and we're starting to see that more and more is how do we recognize that the rainfall patterns are different and the soil moisture amounts are different, and obviously the storm systems are different. We see that the topic is maturing, and so I hope just giving you a few snapshots over time, you've kind of seen the difference in what some of the general research looks like. I think we also have the advantage or the capability now of a lot of bigger data sets. and really just generating point clouds in different methods. And suddenly there's this chance now to have really nice characterization at different time periods of what areas look like. I think there's a lot better modeling, not only on the computer, but also in laboratory or flume studies. I think that things are getting more advanced and people are able to dial in better, what the characteristics are. And so what does that allow us to do now for research? For one thing, there's better runoff and inundation modeling. And Katie had a paper that came out a couple years ago that I'll highlight, comparing different inundation models. So not only are we getting to the point of developing these models, but trying to dial in when are the best times to use each one, and what are the strengths and weaknesses, and where do we need to really focus our efforts. The effects of climate change, what's this going to look like 25 and 50 years from now? Things like not only erosion out of channels, but what does the infilling rate look like, and how are things, the capability of producing debris flows, how's that changing over time? And then a whole different avenue that I really see coming online is risk assessment, whether it's quantitative or qualitative, but looking at this from a standpoint of saying, at the end of the day, we need to manage this for the communities and for the structures that are there. And how can we take what we know and build that into something that the population's using? And there are a few consulting firms that I think are doing fantastic jobs with this, and I really see this as a way for the future. And I'll just say one word, when I first started, I worked in the consulting industry, and we were all kind of engineering geologists and kind of water people at the same time. If you'd had a groundwater class, you were on the water side of the company. Now it's gotten more sophisticated, but it was sort of the early days of doing human health risk assessment, and the RAGs had just come out, the risk assessment guidance for Superfund from EPA, and there was this strong idea that we needed to be able to take chemical data from soil and water and build that into something that had some way of ranking the risk to humans. And what are the pathways that are dangerous, and what sort of cleanup levels do we need, and how can we manage this hazard? And so it wasn't a perfect approach, but it was very, it was very well established what the steps were. And so getting to that point with sort of these geotechnical related risk assessments, I think is going to be really important for us in the future. And then this idea of avulsion, this has been huge for me in the sense that we're talking about alluvial fans, right? And they're built over time by something that's spraying back and forth across the fan. And we're often dealing with this side and thinking about this side. But the idea of how do we incorporate avulsion and predict when and where it's going to occur is important from a hazard management standpoint. And then, again, incision, deposition, this is part of how is a fan built, how is sediment moved through the system. And that's a really important multidisciplinary factor that we need to work with. So what have been some of the challenges over time? And I would say that the first one really is this was considered a subset of maybe some more important research. Okay, we do debris flow work, but over in the corner here is wildfires. And it's part of this, and if you understand debris flows, well, you can add this wildfire component, and there's a few people that are focusing on that. But now, obviously, it's considered a significant portion of the research, let's say 10% of the ongoing research in debris flows. And so that's been a good thing. Measurement of volume, so much of what we do depends on either understanding a past debris flow or being able to predict something in the future. And so this is a study we did a number of years back, and we said, let's look at different ways that people are measuring volume and try and recognize that the number we're giving maybe is a 50th percentile number. And there is plus or minus bars around it that often get lost as these numbers get used. And so I was just looking at things like, truck counts, the trucks are not always filled, or maybe they got a big rock out of the top. And that ends up on a 9 or 10 yard truck. That could be 10 or 20% error. So that black bar, the solid one. Measuring debris boundaries we thought was really nice. We can go out and on an air photo or a map or in the field, we can say, I see this lobe that was just deposited, I can measure around it. Fantastic. And then I need to estimate the thickness. Well, there's a lot of variability, and we actually had some numbers from two agencies, a county and the Corps of Engineers, that measured about a dozen of the exact same flows using this method. Here's the difference in their results. Okay, so we just have to recognize that's the best available, but there are plus or minus numbers attached to it. Slope profiler, we can measure cross sections, and then really what I thought from a scientific standpoint the most accurate is debris basins that have capacity curves in them. And obviously there are little sources of error here and there. We've got newer tools for this, so things like LiDAR and photogrammetry and things that lead to really more accurate DEMs, we can get down to sort of sub-meter level. So I think these numbers are a lot tighter, but that's been an issue over time, is we take the numbers and run with them. But recognizing that that may be a fair source of our error. Another challenge, I think, was there were few consultants with the experience. Plenty of people working in debris flows, but not so many that had a longer history of dealing with post-wildfire and understanding the differences. And I think that's gotten a lot better over the years. Just burn severity maps. So they used to be more what I would call hand-drawn. So it's based on some field data and maybe some remote sensing data, but it took a while to produce the maps. And now you go to the MTBS website, and generally they're producing things within a month after the fire. And I'm sure some of you know this in a lot more excruciating detail, what it takes. But not to say problem solved, but it's we're in a lot better place than we were. Triggering rainfall for these events is huge, and really it's important from a predictive standpoint. And it really started from Nell Kane's paper in 1980, basically one event, and saying, look, we can describe a rainstorm in terms of intensity and duration, and looking at sort of the history of a watershed, which combinations of those two caused debris flows and which didn't, and we, meaning other people, draw a dividing line between those. And so he had this one, and then later on, Sue and Jerry DeGraff published a paper that accumulated a lot of those that were already out there in the literature. And a lot of these had come from an Italian publication that had sort of, it was a meta-analysis that summarized. But it gives you a sense, every drainage basin or group of drainage basins has got to have its own. This is how many were out there at the time. And so we're learning more about it. And then the colored ones were ones that Sue and Jerry put in there for post-wildfire. And so you can already see how much lower the threshold is in both intensity and duration to actually cause debris flows. And now we're starting to see papers that are talking about what's the recovery? How does this line then go back to its previous risk level? And then, it seemed like it was hard then to model probability and volume and run out. And so I've got a few examples here. This is one that one of my students put together using the methods on the USGS Postfire website. And so on the left is a probability model, and the center is a volume model. And these can be cranked out a little bit faster now. There's sort of a protocol for doing this. And then, again, run-out modeling has been difficult, and now we're getting to the point, I want to plug this paper again for Katie. I just think this is a fantastic look, a really rigorous study of several different run-out models, and really looking at where is the error, under which cases are certain models more effective and certain models less effective. And so this is really what we need, is these types of studies that are helping us be more granular in how we approach this. Another set of challenges that I think has been it's been really kind of sticky. There's a little pun in there. Is how do we deal with viscosity and yield strength? And so there are a number of models that require that, or a number of our sort of analyses that try to think of this. And first of all, recognizing that through the course of the flow, the different parts of the flow, these are going to be very different characteristics. But we've got to pick a number at some part of the flow that we're using. And so in this example, I had a master's student that went through and did a whole bunch of lab scale tests, not with a viscometer, but with something that he had rolling sleeve viscometers, and he had flume tests and 4 different methods of trying to measure these. And it's a huge amount of work. And so basically what he's showing on the y-axis is on the left one is yield strength, on the right one is viscosity, and then the x-axis is the sediment concentration. And so saying, okay, as we increase the percentage of sediment, did this by volume just because of the way it worked out, and then each curve represents a different grain size fraction. So the leftmost curve, the blue one, is everything that passed the number 40 sieve. So pretty fine material. And then you start adding in coarser and coarser material. So there's a series of tests for each of these just to try to measure this parameter. And you know, by the way, for viscosity, everybody uses 2 to 3, and that's sort of in the middle of the graph there. But the complication of adding coarse material, and so he did all that work and got up to a 1-inch particles. And so this required a pretty big viscometer to measure it. But imagine then going from that to, let's say we're going to include boulders, we're going to include cobbles. So we've really, I'd say, not only measuring those, but sort of how do we incorporate these larger fractions. And if anybody's interested in this, I'll send you the thesis. I thought it was a great study, but it's a little bit complicated how you add in this coarser material, and we kind of get up to 1-inch particles. So if you got a debris flow with 1-inch particles, this will be really helpful for you. But for the other 99.8%, we need more research in it. So how have our concerns changed over time then? And so there have been different geographical focal points. I want to start with this base map that's just, you've seen versions of maps like this, but this gives you a sense of where are fires occurring over time. And you can already, I think most of you are probably already looking at Africa and thinking, gee, I don't know of any post-fire debris flow publications in Africa, even though that seems to be the area where the red blotches are. So the early studies seem to really center around Southern California, and there's a few at other places. And in fact, really in the LA basin. Over time, those expanded to incorporate the arid Western US. Then they expanded to incorporate the Pacific Northwest and Canada, and you start seeing publications there. I don't know if it's just proximity of researchers or what, but it's being infected, right? And this virus of post-wildfire debris flow studies is expanding across the world. And then you start seeing some, and I believe that the map that Luke showed had a lot of these similar things. Spain, Italy, maybe in parts of Southeast Asia, Australia, and a few others here and there. But so the concern over time now is that there's a recognition that this is happening worldwide, and I think there are just more researchers becoming aware of that specific element of debris flow studies. I would say that some of our focus has changed from volume modeling to runout modeling, and there's still plenty of work to be done in both of those. But the paper on the left there is by Joe Gartner, and some of the results that they're using in a lot of their hazard analysis right now. And the paper on the right is this runout modeling, to give you an example that I've already talked about. And then I would say there's been a shift over the years from just hazard response to prediction and preparation. And so on the hazard response thing, This is a publication from 1925 by, the person's last name is Paul. This is not me writing this. Talking about the floods of 1923 in northern Utah, which actually caused them to build a bunch of debris flow basins there that you still drive across when you're driving the Wasatch Front. And they talk about some of this hazard response, and really the main suggestion they give is revegetation, and then there's a little bit of capturing the material. And then as we move towards the diagram on the left, I just pulled this off of the website, but we're producing a lot of these maps now that help us to say where are the worst areas, how can we predict what might cause an event that we need to do something about. And then I'm going to spend a little bit of time talking about mitigation methods. And it seems like some of the stuff that's really appeared or gotten more deeper studies recently are things like catchment fences and hillside treatment, warning systems, and risk assessment. And so, again, going back to the control of nature, they quote LA County post-fire protective advice sheet. Okay, so 1989, this is obviously something that was published a little bit earlier, probably in the 70s. It didn't really say, here's your options. Construct a pipe and beam deflector, board your windows, consider evacuation. The fourth one should have been pray, but these aren't a lot of really great options. So I wanted to look at some manuals that, or publications that aggregated mitigation options over time. So in 1971, this is HEC 9, so this is Corps of Engineers, basically thinking of it from a surface water standpoint. They have these options for mitigation, and I think they all fall into these 4 general categories. So there's some sort of deflection, trying to control where the flow is going. Interception, which is, I guess, smaller scale version of things like dams. And then basins at the bottom, where we capture the material. And these are all great methods. They're effective, but that was sort of the state of the art during that time period. We'll move forward then to 1996. Doug Van Dyne published a debris flow mitigation manual for BC, maybe in Canada. This is available online. It's a great manual. And he gives a lot of options. This is just sort of a snapshot of a screen capture of the index. But they seem to fall into 4 categories again. So we've had a certain amount of time pass, and we're getting, I'd say, subsets within these categories, but they all sort of are those general mitigation schemes. We did a study then a few years later, really trying to link mitigation schemes to socioeconomic groups. And so what would be effective just for debris flow mitigation in Guatemala or in the Karakoram in Pakistan. And then we also use Southern California as our examples. And I've circled a few things that seem to be a little bit different categories from things in the past. So maybe a focus on education. And so popularized sayings that show up in the newspaper about after the fire comes the flood, that sort of thing. Maybe there's preset warnings, there's fact sheets that come out. And then avoidance or other warning methods, sort of prediction methods. Cable fences started to appear. So these fences that have been used for rockfall, suddenly they started realizing you can use them for debris flows. And one of the first people to put those two together was John Duffy with CDOT, or CDOT, Caltrans. And I just heard from Jerry Higgins yesterday that he passed away from a heart attack just recently. And then things like hillside treatment and recognizing if rainfall, erosion, water runoff is the problem, can we reduce those effects? And then Emily Mose had just this fantastic thesis that came out of Canada, and she's looking at some different approaches like debris regulation and this sort of management of the material, and then response planning and this risk-based approach. And so we're starting to see these new categories that are giving us new tools to add to the toolbox for mitigation. And then finally, this idea of climate change effects, and what does that do? And I want to just give you an example that we did from the Thomas fire. So we wanted to say, if that fire occurred 25 years from now or 50 years from now, how would the effects have been different? And so the Thomas fire was the one, the debris flows afterwards, went into Oprah's yard and it killed 20-something people. And so this is I think a big impact on the psyche of the US, and this is going to be an important event. So we said, how is this going to change? And really there's things like rainfall and the size of fires that are going to be changing over time because of the climate. And so there are a few different models looking at the increase in burned area. We chose the third one down, the gray one, and basically said by the year 2050, so roughly 25 years in the future, it's about, I can't read the numbers, but it's about a 54% increase in the area, burned area. So maybe we can do that per fire, maybe it's the entire Western US, for example. And then in 50 years, in 2075, it would be like 81% larger. So these are much bigger. What this looks like on a map then of that fire, the inner polygon, the blue one, is the actual fire perimeter. There's a little island in the middle that didn't burn because of some of the geology and vegetation differences. And then when you get to 2050, the year 2050, it's that yellow, so that's 54% larger, and then the red is 81% larger. And so you can see if you just expanded it kind of evenly all the way around, suddenly we have a much bigger fire footprint. And what this would look like in terms of a hazard then is the first column is the year, the second column is based on some climate prediction models, how much bigger would the design rainstorm be, or the typical rainstorm that's occurring. The third column is how does that change the fire size? So those are the numbers I've already talked about. And then the fourth column, how many more drainage basins does that include? So the actual fire was roughly 1,700 basins, and by 2075, we would, that same sort of fire would impact twice as many basins. And so it's just kind of a way to look at this and say, in the future, how much is our problem expanding? Then after that, we said, well, what's the volume of debris coming out of those basins? And so he ran, the grad student ran a predictive model for every one of these and added it all up. And we said, okay, the predictive model would say something like 111 million cubic meters of debris, and it's going to be more than double that. So you're in an important research field. This is just going to get worse. And then finally, the last column said, of those burned basins, there's a certain percentage that are considered high hazard. Well, that percentage is going to increase over time because of intensity of burn and the rain that's falling on those. So next, the organizers asked me to look at what are the things that we're doing that we shouldn't be doing. And so I sitting in my office, I thought, why are we still doing this? Well, one is, why are we taking our data sets and applying them outside of the area where they're originally set? Or the predictive models, why are we applying them outside? And the reason is because we don't have that much good data to use outside of that. But just to recognize, so a lot of what we're doing is based on some of Joe Gartner's work. Here's where his original data came from. And we're trying to extrapolate that out to bigger and bigger areas. And I think we're getting a lot better at seeing the distinctions about having other data sets, but it's an area to be careful. This sense that we're neglecting avulsion, and to me this picture is one of my favorite debris flow pictures ever. And it's from Santa Quin, Utah. Rich Giroux took this. You're basically up on a hillside looking straight down the fan of this neighborhood. It's a bright day. You can see where the debris flow came down. That road that heads sort of away from us on the left, that's going directly down fan. And it's not tremendously steep, but it's going down fan. That's a super obvious path for a debris flow to follow. And so the debris flow came in from the left and it heads down that road, and you know, if it was a little kid, it'd be running with its arms in the air, and it's like, I got this free path, down it goes, and then mysteriously took this 90-degree right-hand turn. What happened there? Well, what happened is that road, even though it's going down fan, is not the same angle the whole time. Where it intersects the other street, it levels out, because that's what we do on road design. And so it leveled out, the debris flow slowed down a tiny bit, and the back part of the flow just zipped around it, because even though it had only slowed down, let's say a few kilometers an hour, if you're in Europe, a few miles an hour here, the rest of the flow felt like, oh, there's an impediment, there's a dam in front of me, and it shoots off the other side until it gets to the next intersection and makes another turn. And so imagine then the surprise of some of those people out there, the bad luck for this kind of random avulsion pattern that caused hazards for them. And so I've been doing a lot of studies, kind of nibbling around the edges of this, trying to understand it better and predict it better. And so this is a debris fan from the White Mountains in California. And this was basically a map over time of some of the different debris lobes. And so clearly, every time that we get a new lobe, it's because there was an avulsion, mostly occurring pretty high up in the canyon. And if we were to do a single run-out model, we would probably follow the current lobe and probably deposit material on that. And so among other parts of the study, we went in and looked at if we put a physical barricade, just kind of modified the topography to put in and force an avulsion where we predict it would be, where would the flow go? And so, you know, I guess this is confirmation, but it's pretty easy to say, well, yeah, it's going to jump onto one of the previous lobes. And so you can see the one on the left followed a different lobe, the one on the right also did, but it's a different fan, and it actually comes back parallel, and some of them rejoined the original flow. But just to say that if we're modeling run out, we cannot just focus on the current situation. We have to recognize that dams and avulsions are occurring, and are we prepared to mark those areas? And so if part of this, the grad student, and this is a paper that just came out, had come up with a predictive model. There are various ways of looking at this, but just to say, look, there are ways that we can sort of capture what might happen. And so using this method, she was able to predict about 2/3 of where avulsions were occurring. I think we're also having a hard time with bulking factors and discharge. And so if we consider discharge as the value Q, and that just says how much is passing a certain time in cubic meters per second, cubic feet per second, and that helps us design things like culverts. So there's a picture on the left there. The grad student there's no way he's going to be able to lift that culvert. They've made it a pop top to clean it out. So their solution was, instead of building it big enough, we'll just recognize it's constantly going to get clogged, and we'll just be able to lift the top off with a forklift and clean it out. How big does that culvert need to be? Or if we're putting in barricades along the side of a road temporarily, how much capacity do they need? And so we have this Q value, and the idea is that if that's what the flow is for clear water, we recognize the flow volume passing per unit time is going to be bigger for debris flows, and we'll have some bulking factor B to come up with this Q for debris flows. And so normally then this is done empirically. It tends to be region specific. The value that gets used a lot is 2 to 3. There was some early publications in the 70s that proposed some of these values for Southern California, and those seem to get carried through the literature a lot. And there are other ones that are a little bit bigger. But we felt that we needed to have a better handle on this. And so Holly Brunkel went through and tried to assemble a database of sites where we're confident in the accuracy of those values. And then she divided them between burned and non-burned areas, and then by size of drainage basin. And so you can see bulking factor instead of 2 to 3 tended to be, well, look at the averages. Smaller basins, unburned, 10. So much bigger than 2 to 3. And as the basins get larger and larger, you start dropping down in size. But I found it pretty unusual to have to deal with a basin that's 5 square kilometers. I mean, that's really gigantic. But certainly much larger. And then you get to the burn ones, and they're, you know, a couple times even bigger than the unburned. And so this is a huge area. So if we're designing bridges and culverts and you know, conveyance channels and things for debris flows, we need to recognize that it's bigger than 2 to 3 times what the clear water flow would be. I'm just having a great time. These are like all my pet peeves. I always say that, you know, a scientist studies something because they're curious. An engineer studies it because they're annoyed. And they're just like, why can't we get this right? This is something we should be doing. And so one of them was predicting debris flow velocity. And we use this force vortex equation a lot that basically just says when the flow's moving and it's banking a little bit on curves, we can get a velocity from that. And it requires that you know the banking, and you have to estimate the radius of the curve and things like that. And so Adam Prochaska went through and looked at this and said, look, even under the best circumstances with the best data, this radius number has some variability in it. And so maybe these numbers are not as accurate as you think. And so the left-hand diagram is from a Utah Geological Survey publication, and you can see the variation and the sort of the error bars on this velocity. And then that center one was Adam had plotted this looking at velocity for some published values and some of his for what the Reynolds number or the Froude number was. And so basically the assumption to use this equation is that it is subcritical flow, so Froude number less than 1, that tells you about the level of turbulence. And just roughly looking at that data, half of the values used sort of violate that principle. And so not to say we have to throw out this tool, but we have to, you know, use it with sort of a grain of salt. Now finally I want to talk about a few surprises. The star of the show seems to be Joe Gartner. Here's a picture of him. And so it's not just mud and logs that are coming down here. We're up in a canyon above San Bernardino. You can see the city down below. And I'm literally taking this picture and thinking, we may be the first human beings that have ever come up this horrendous slope. It's so difficult to get up here. And come down the next canyon and we find a skull. And that was post debris flow. So this thing was only a few months old. And then I don't know if it was the very next time we were out there doing field work, but Joe and his brother encountered another body. And so, and both probably drug related, and you run into like evidence of pot farms and things. And so this is, there's a lot of things other than just straight debris flow science out there. The rate of regrowth has just been just stunning to me. This was literally just less than 6 months after the fire. If you didn't see the burned sort of manzanita trunks and you were just looking at the ground, you wouldn't know this was a fire. There were vines that were 2 meters long, 3 meters long. And so we did some studies related to this. I don't want to get too much into the weeds here, but the x-axis is basically different time groupings. So Western US, less than 1 is less than a year after the fire, 1 to 3 years, and then all the way up to greater than 10 years or unburned. And then the y-axis is basically a representation of volume. It's normalized by basin area, and then we took the log of that. But you can see the box and whisker plots. They're evened out a little bit because it's log scale, but the rightmost one, less than 1 year, is a little higher, the median's higher than the rest. And statistically, it's different from all the rest, and statistically, all the rest are the same. So if you look just at this number, it would say the recovery after wildfire is 1 year. Now, I'm not willing to say it's 1 year, so I say, yeah, it's 1 to 3, something like this. Andrew Grabers has a great paper that's going to be coming out that really dives into this and gives you much better information. So if you have questions on this, ask him, go see his poster. It's in your poster on this one, right? It's there right now. So you can sneak over there and ask him questions. But it occurs quickly, and that's just always astounding to me. So here's just an example of a site that's less than a year, and you already see stuff coming back. 1 to 3 years, the ground cover's coming back. And this is Western, right? It's not going to be 100% ground cover. So this looks a lot like what the permanent ground cover is going to look like. A few years later, it's getting a little thicker, and then finally this was the Storm King mountain fire in western Colorado, and you could see some of the scars there, and actually these steep scars are starting to revegetate. So it's been a real surprise to me. The importance of scour has been important and has been kind of stunning for me. And this was actually from my master's thesis years ago. It was not fire related, but it was in Davis County, Utah. And at the left, there was a small landslide that started this debris flow. And then as you go down the canyon, you can kind of see what the scour looks like. And there are other areas that just have huge amounts of scour. There's a lot of sediment that's coming out of these canyons and a fair amount off the hillsides as well. If you look at measurements of this, this graph basically just shows you the cumulative volume as you move from the top of the channel down. And we have lots of examples of this, and other people have produced these. But you can see how much of the flow is occurring as this thing goes. And some of these have really important thresholds. So you can see that star, there's sort of a kink in the middle where the accumulation rate of debris just takes off. And we don't completely understand why that's happening. And Lauren Miller has a poster that's going to be up that talks about this, and any feedback you can provide on that will be really helpful. You know, a couple other things. It's always surprising to me how little water is required. These storms, these 2-year storms and smaller things are actually causing post-fire debris flows. The thresholds are lower. We did a water balance. Each column there represents a different canyon, and the colors, ooh, Lord. So the blue is how much water was incorporated in the debris flow. The red, the middle bar, is how much potential infiltration of the rainfall there was. And then the top bar, the green, is how much runoff there was. And so this sense that it's a dry system, we start adding water until we get enough, and then we have a debris flow. I really think the model is there is way more water than you need. And the debris flow only uses a small portion of it. It really depends on the intensity, and that's what's causing the thing. And then we wanted to look at antecedent moisture. And there's some places that require it and other places that don't seem to do it. This was a small study that we did, and the middle column just shows how much rainfall was there in the previous week and then how much in the previous month. And so some of them had a fair amount of rainfall, but a lot of them really had hardly any rain. So it's a pretty dry system. Rain comes down, boom, post-fire debris flow. And then there's this final kind of thought is how fast these things occur after rainfall. And so these pairs of graphs, the top one just says we had a pressure transducer so we could get the exact time when a debris flow passed, and then below it have a rain gauge nearby. And it's basically plotting the cumulative rainfall, and so where the steep curve occurs, that means there's an intensity burst. So intensity burst, and really just within a few minutes, you get a debris flow. We are not the first to do this. Here's some examples that Sue Cannon had published. And again, steep portion of the rainfall curve, blue triangles where a debris flow occurred. And so there's a very quick reaction. So in summary then, I really feel like the research has accelerated. As we all know, it seems to have taken off in the 1990s. I think our focus has shifted from the basic questions you would have in any research field, you know, when do these occur, how big, where, to things like who gets affected, what gets affected, and then to things like, well, what does the future hold for us? I think we're getting bigger and better data sets, better monitoring, better modeling. We're incorporating important effects like climate change. These are occurring in locations that were previously not affected by this. And then finally, I think mitigation is advancing, but surprisingly slowly. So with that, I will conclude, and thanks for your attention. So apparently we have time for one or two questions. Yeah.
I'm curious a little bit about the terminology in regards to your first topic of like the history of this whole subject. I remember reading years ago about those reports in the 1930s in LA. Can't remember what terminology they were using. Then I remember assessing the Soberanes fire in Big Sur area in 2016. Reading some publications from the 80s or 70s. And obviously they were not using the term debris flow yet.
Okay. Yeah.
I'm just curious how much attention you pay to the change in the term.
Right.
And if that affects by any chance that.
Right. Yeah, so the question for the recording is basically the terminology and were we capturing all those. And I would say no, we were capturing something a little bit different, but I would say it proportionally, it didn't change. Now it did, I think anything that was flow and fire, it was capturing that sort of stuff. Now maybe it wouldn't have caught mudslide. Maybe it wouldn't have caught burned. You'll have to go to Luke's future paper. Because I could already tell what he was doing was a lot more granular than what I was looking at. Thanks, though. Other question?
Carry that in my hand so I don't forget to turn it on.
Oh, no, please go.
Yeah.
I'm wondering
Like, Don,
what
put
is the
that thing on.
spatial threshold between post-fire debris flow to post-fire flooding?
The spatial.
Like the threshold, like I mean, the post-fire debris flow probably mostly occur in a scale less than 5 or 10 square kilometers. And then, so when the like flood magnitude, when the watershed magnitude gets bigger,
Right.
they don't need to worry about the post-fire debris flow within.
But more muddy flood.
Right, and then
I would assume that's a valid observation. I don't know specifically what the difference is, though. As you get to bigger basins, is it more likely to have a flood response than debris flow response? Write that down for your group discussion. Thank you.